So in a previous video we solved the Poisson equation, it's this guy, and in this video we're going to try to do some fluid dynamics with it. So we're basically going to look at this incompressible Navier-Stokes equation, which looks like that. Actually we're going to simplify it a bit. We're going to remove these last two terms and only have left hand side and that one, this, yes. And the reason we need the Poisson equation is that this quantity P is determined by a Poisson equation like this. The right hand side doesn't depend on P at all, so that's why it's like a Poisson equation. And I think this video might, or this project might be a bit long. So this video might be long, or it might be several parts, it might be several long parts. But let's see. So I have copied the old Poisson equation code to a new folder that I called the Fluid Dynamics. And let's just see what we have so far. We have this gradually solving the Poisson equation and visualizing it in some way. And it's quite nice actually, like this kind of pixelated look I like. Can we make it slightly bigger? Like, what if we say 1200 and then it's 225, 675. Anyway, so let's have that. Right. I think there was one bug, which was, there's one thing we can change. We are basically rendering pixel by pixel right now, so we don't need this square with stuff. And here we can say SDL render draw point, and we draw at ij, ji, but actually not I, it should be the height minus 1 minus I, because we kind of have a flip coordinate system. So that didn't work because this line has to be commented out. That also didn't work. Cannot assign value j of type u. 68 to int 32. So perhaps we just, maybe we can just omit that type here. Let's see if that works. Okay, so we actually need 32, and that causes issues there. So I think what we're gonna do is keep this, just keep it simple for now. This is probably not the most optimal way, but then we're gonna cast it here. Like so, run it again. Now it's working. Okay. Just a small optimization. We're drawing points instead of rectangles. So, anyway, what do we need? What do we have? We have a main, we have a field, and we have the Poisson solver. And right now in each half second or something like that, I think. No, just like in each iteration, we are doing a Gauss-Seidel and then visualizing it. I'm surprised it takes that long then. That's a little bit worrying. What if instead of this, let me maximize this. We don't need to look at Wikipedia right now. what if instead of this we disable Copilot? We called this function not Gauss-Seidel, but solve. Just called solved. Solve. Let's rename it to solve Poisson because we're gonna have many different solvers in this project. So we solve it for that field and that source. And there we go. Actually, can I make a field, make a random source? Just want to see if can I do like what it, okay, let's check inside the, this is the source directory for Odin, so let's check for if it's possible to seed the random generator. So there's a set global seed. Let's try that, just because I want it to look the same every time. So now it kind of converges to something like that. Let's see if we can remember. And it looks similar to me. I think it's the same every time. Now my question is, why does it still change? Why doesn't it just use one? It's because it has a max number of iterations, probably. Let's print if it converged. So it does claim to have converged, but it's clearly changing. So why is that? Could be that this one has to be smaller. Weird. Maybe the error is not correct. Let's try to make the error even smaller. Let's remove that. Let's put 500. Put 1,000. So it's quite important that we can get it to just converge with one call to solve Poisson. Maybe there's something wrong in how we calculate the error. Yeah, I think I know. We need to take the absolute value. At least something like that. Let's try to run now. Right. So that looks a lot more correct. It takes a while, but then we want to make that almost instant. That somehow didn't feel much faster. Okay, so that was a bit better. Let's try this. There are techniques we can I actually wonder why it looks a bit different now. It's kind of weird. Let's keep it at 100 because that seems like it was. It's not quite enough actually. Let's put 500. So here it seems fully converged, but it has like a noticeable delay, which may make our animation not so nice. But it is what it is. Okay, so basically we need this V thing. So we have this concept of a field, but now let's make something that we call a fluid. I'm gonna make another file called fluid, and probably these two packages would be good to have. So 2D fluid is again a struct, but what does it need to have? It needs to have Vx, Vy, it needs the pressure, and it needs a density, which is just a single number because it's going to be incompressible. And then we'll put a width and a height. Let's try with integers now, see if that, maybe it's a bit silly to change it too much. I wonder if this guy is gonna break. It's actually assuming we have a field. So maybe we want to reuse that. Like we have the two guys of these, and then we can put in a field, but it will have some. I wonder if you can treat this as a pointer. Because then we could make a view on the field. So I think we're gonna try that, but let's just continue for now. Well, let's write that. So for this equation, there's a couple of steps. So it's a time-dependent equation, it's a dynamic equation. So you have to sort of solve for the next time step given the current time step. And in that process, the first thing you do is find the right-hand side, which in our case is just this term here. So we need to solve this Poisson equation in each time step. So let's make a function that sets this up and solves it. So call it find pressure, and it should take a fluid, not field, but fluid 2D, and then that's about it. It will modify the object, the structure, the data inside the fluid. So let's start by making a field for putting into the Poisson solver. Right. So the data is gonna be the pressure of the fluid. The width is gonna be the width, and the height is gonna be the height, and the dg is gonna be the dg. So I hope that this should work. Let's try to compile it, and syntax error, because I keep forgetting that this is how it looks. Right, so let's do U64. But it works, so that means that, and I don't think this is copying data. I hope not. Let's actually copy this this kind of logging allocator that I have in one of my other projects. So we're gonna need, just to check, we're gonna need this guy. We're gonna need all these allocator functions. We're not gonna keep this, it's just to test something. Let's get rid of that. This one we want. So this we can like enable an allocator. So let's say context.allocator is equal to my allocator. And how is it I use it here? It's like that. So let's do this and my allocator. And it takes the data, and that should do it. And then we need to do something like print line entering, so we know whether any allocations are happening in here specifically. So let's go to main. Let's make a fluid. Actually, let's make a function that does that. So here we go. And it won't do anything, but it will return. It won't take any arguments, but it will return a fluid. And that will be fluid 2D. So it needs Vx and Vy. It needs a pressure. It needs a width. Actually, that's probably an input argument. And it needs a dg, which also should be an input argument. Then we return the fluid. And that's it. So, U64, dg, fluid 64. And in main, we can just use this guy, field width, field height. And let's also make a variable dg, like so. Right. So now we need the Vx, the Vy, and the P. So Vx is some kind of array, which with this capacity. And actually Y and P are going to be the same. And that's it, I think. Let's try to run that. It did not work. We need format for the logging allocator. And somehow that didn't work. Ah, you need the reference just. Then we also need OS for the logging allocator. Alright, so now the make thing. Right, so we need to actually say fluid is fluid.make. Or is it new? How do we do it in field? Here we say new. Right? Yes. And then here instead we're gonna do do something like substitute from, how do you do that? Okay, just remove that. Right. And here we're gonna say substitute the end. No, that's not the end. This is the end. How do you do the end again? I don't know. It doesn't matter. Let's just say, let me redo that. So the equals we probably want. Actually, why am I making it way more complicated than it needs to be? Just do fluid dot whatever, and that should be it. So we run that, expected semicolon got equals. Okay, so that's working. So now we have a fluid in here, and then what I just wanted to check was if we call this find pressure procedure, what will happen? It will not do any allocations. So that's very nice. I kind of feel like this allocator is so useful just because I'm not so familiar with Odin that I'm actually gonna grab it and put it into a separate file that called login allocator, and because we might have use for that in other cases. So let's go make login allocator. It's a procedure, it doesn't take anything, and it returns an allocator. And it should essentially do this stuff. This stuff. Let me somehow get out of that one. What was I gonna do? I was gonna do this. Right. Maybe you can do something clever so it automatically prints this, but I am not going to worry about that right now. So we may do that a little bit later. Anyway, so now we have just the data set up. We also need the source. This is what we want to find. Let's also get the source. Now the source is a bit more complicated because we need all of these operations. So let's first let's try to get this gradient thing. It doesn't really live in here. It should probably be in here. This I don't want anymore. Let's get rid of that. And just reminds me of something. Let's have a defer delete fluid, and delete fluid. It's a procedure that takes fluid, pointer to fluid, and it will delete these guys, and then it will free the fluid pointer, something like that. Okay, so let's go in here and let's make a function that takes the gradient of some kind of field. So the question is, where should we store that gradient? And I don't want to return, I don't want to like make a new storage space for it all the time. So let's also have a destination field, which is where you can store the gradient. And now we simply do that. Okay. So let's say let's call it row in 0 to field.height, and it's less than the column. The index is row times field.width plus column, and the data at that index is something. So for now we'll use fixed boundary conditions. I think that's what we used in the Poisson solver. Yes, pretty sure. If this is less than that, then we do it, otherwise not. That does indeed look like fixed boundary conditions. So let's stick to that. This basically means that if you try to look at what's outside the image, we just consider to be 0. So let's try to do that, and let's call it df dx. So what we want is like I'm a little bit annoyed by this. Let's try to do something like this. Actually, let's do it the other way around, because the column is the x and the row is the y. So I just want to return let me see if this even can compile. There's some problem in here. Right, remove that one. And now the allocator is complaining. We also need format. Right, so I was worried about this. I don't think you can capture variables like this. There was something about that. So that's sad. But whatever. Because what we need to do now is df dx is equal to the destination at the next point minus, sorry, not the destination, but the field, minus the field at the current point, and then all of that divided by the dg, the grid spacing. The same thing with y, except now it's this, the row that is indexed, incremented, and then the data at the destination. So, okay, this is, I didn't think about this. Because it's the gradient, we actually need two destination fields. One for the x component, one for the y component. Right. So that's it. That is basically it. Now we just need to handle all the boundary cases, the edge cases. And how will we do that? And possibly there's a better way to do this thing. Actually, let's do something like this. So if column is greater than 0, column is less than field width, then we will do not this, but this. Else, if the column is greater than 0, so let's say this, we're on the left. So now I'm doing like kind of like a central difference instead of a right difference. So instead, if the column is 0, and let's also declare this thing actually. Then we're gonna assign it to not -1 because that would be out of bounds, but just let's delete it. So if we're on the left side, we do that. Otherwise, we are on the right side, and we will instead do this. Actually, let me copy paste that one. So there we go. Now we just need to do the same, but for y. So let's say substitute x with y. And let's also substitute +1 with nothing. And substitute -1 with nothing. And then this was +1. This was -1. This was +1. And this was -1. Of course, this has to check on the row instead. And the height. So let's see if it compiles. It does not compile because I just said field, and it has to be field field.data. Something went wrong there. Field. Replace that. Is this like a special character? Replace that. Okay, there we go. Replace it with field.data. I like that. Ah, and I forgot to field that one. Let's try to run that. There's nothing called RWO, it's called row. Okay, compiles. So let's also try to run it. Let's solve the field. Let's make some more fields. Let's just make some more fields. So we call it the X field. Right. And then here I want to get the field and perhaps render that. And that failed, so there's it's always good to test. So here we loop row column less than that. If column is, and it should be not less than, it should be less than -1. Of course. Let's try to run it again. So now it did something. It's hard to tell if it's correct. I'm gonna grab some other code. I'm going to grab from the Nelda Meat project. There was like, this one, save frame. So let's try to get that one. And then I think we can even just say, okay, so now after visualize it's on the renderer, so we can say save frame, and we'll call it dx.png, and look at the renderer, and then we can actually visualize it again, put in the field, and we can say save frame, call it field, and just for fun let's also save frame source png renderer, and let's try to run that. So more or less correct, did what I visualized, what I expected at least. Let's comment things out, and let's now check. So we got a couple of PNGs here. Can I just open them all? So it's a little bit hard to see. That one we don't need to look at. So for example, in this, let's say, in this region, there's like clearly a change from red to blue. So we also expect like there's a horizontal change from red to blue. So we also expect a high value of the x derivative. So that's the wrong one. And it does have a non-zero value, it looks like. And then, so that is going from red to blue, so it's apparently blue. And then over here, it's going from blue to red, so it should be red. And it is red. Here there also are some, it's quite hard to see in this visualization actually, but I guess like here it's very strongly blue, it becomes less blue, so it should be red around here, and it is red. So I think it's correct. So that is pretty good. Now this is only the start, and perhaps this way of doing it is not the nicest. Perhaps there's some kind of honestly, I don't know. I don't see any better way to do it right now. But here we are now, we have the gradients. Then actually we want to also calculate this thing and then the divergence of that. And this is also the gradient of the velocity field. So perhaps it would make sense to write this out. So, nabla v is, let's say v dot, that is vx dx. It's a vector. So it's going to be something like this. Dx again, but dy now. That's the first component. And then it's going to be vy, y, d, sorry, x, I think. I think that's correct. And then we want the divergence of that. So that's basically d of all of this thing, dx, plus d of all of this thing, dy. So it's not super simple, and it's quite possible that some kind of incremental approach is not the right way. Maybe it's better to just calculate it at once. So let's see. We use the product rule on that guy, so it's going to be this. It's going to be this, and the same thing here. We'll have a dy dx term plus squared term, and it will be quite similar for the other guy. And this was a mistake, because all of these should be y, dy, dx, and this one is dy plus so I don't think that is too wrong, but obviously it's quite complicated. But we need the second derivative, we need the first derivative anyway, so... And then we need this mixed derivative. So maybe we're gonna stop here, and in the next video we'll probably work on these other derivatives, like... Let's call it I don't know, I think it's called a Hessian. Hessian matrix, there it is. Yes, the second derivatives. So it should take a field, and it should return an XX derivative, a YY derivative, and because we're dealing with nice fields, XY and YX is supposed to be the same, we're going to assume they're the same, and then it will do something. All right. I think that's it for now. And this function is what we're going to do in the next one. And it will probably use this somehow. But yeah, that's it. See you in the next one.